Okay, so we're going to go over solving equations, right? Trigonometric equations. So let's start off with the basic one here. All right. And let's say we have cosine of x equals to negative root 3 over 2. Okay, so we see here we have this is one of a basic angle that we see in our unit circle. Okay, now in the previous section we talked about inverses, so we could kind of treat the inverse like almost like an operator, where if we take the cosine inverse of both sides. All right, and then we learned in talking about inverse functions that this essentially cancels each other out, and we're left with x equals to the inverse of root 3 over 2. Remember, the cosine inverse is an angle between 0 and pi. Root 3 over 2 would correspond to pi over 6. Okay, and we'd say, all right, wow, I found a solution. All right, but now let's take a look at the graph, right? If we kind of interpret these as two separate functions, right? The y is equal to cosine x and y is equal to negative root 3 over 2. And excuse me, negative, I forgot the negative there. So we're looking at one in the second quadrant. So it's actually 5 pi over 6. Now, if we take a look at these graphs, right, where the first one, we have cosine, let me use function notation, cosine x, and square root of 3 over 2. Let me make that a negative. All right, let me adjust the window here. Okay, we get a nice big graph there. Now we notice here that we have several solutions, right, just in the window alone. The inverse only gets me one of them, right? So we have to figure out how do I find the rest of these solutions, right? And we use that knowing the what we've learned about the cosine function, that it is periodic, and also where the cosine is negative, right? That being the second and the third quadrants. Okay, so let's go back to our paper here. All right, and this is really just a starting point, right? We did some good work here, but now we need to expand on it, right? We need to bring in our knowledge of the cosine function. So we know that it is negative in quadrant 2 and in quadrant 3, right? In both cases with a reference angle of pi over 6, right? This being the reference angle here, right? So the first angle is 5 pi over 6, which we get from our inverse, right? And if we were to use a calculator, it will give us the 5 pi over 6, or 150 degrees if we're in degree mode, right? But how do we come up with the other ones? Well, if the reference angle here is 30, then it's 180, or pi over 6. Then we get pi and another pi over 6. This gives me 7 pi over 6. All right, so now we have both of our angles here. And remember, these angles are between 0 and 2 pi. But I know that the period of the cosine function is 2 pi. So these solutions will repeat whenever I add 2 pi radians or subtract 2 pi radians. Right? So to represent that, we're going to have two equations here, right? So x is going to be 5 pi over 6 plus 2 pi k, or x is going to be 7 pi over 6 plus 2 pi k, where in both cases we need to make the statement that k is some integer. Okay, we need to make that statement because we need to say explicitly what is k, right? It's not any real number, it is specifically any integer. Okay, so let's look at just the graph so we can kind of confirm that these solutions do give us, or these equations do give us a solution to our equation cosine x equals to negative root 3 over 2. So let me switch over to the graph here. All right, I'm going to plot these ordered pairs, right, where my x-coordinate is this 5 pi over 6 and plus 2 pi k. Let me go ahead and add a slider to that. And I can type in an ordered pair here, so the y-coordinate would just be the function evaluated at 5 pi over 6 plus 2 pi k. All right, let's step of 1. All right, we can see here when it's 0, we get that 5 pi over 6. Okay, now let's plug in the other one. The other solution we got was 7 pi over 6 plus 2 pi k, and the function value evaluated there at 7 pi over 6 plus 2 pi k. Okay, and now we see when k is 0, we get the the solutions that lie in the second and the third quadrant, that being 5 pi over 6 and 7 pi over 6. And as we let k be, let's say 1, we get the next values, right, where we add 2k. 2 pi k, excuse me. Let me zoom out a little bit here. Oops. All right. Let's see, the x, let's go. Okay, when we let k be 1, we get the next when we add 5 pi over 6 and add 2 pi. So that gives us 7 pi over 6. And then the 7 pi over 6, when we add 2 pi, we're at 19 pi over 6. Right, and we see that as we let k be 2, that gives us the next solution. Right, in the other direction, the negative direction, we see we get all those solutions there. Right, and as we zoom out, you can see that, you can see that we'll have an infinite number of solutions, and these two equations that we have, those represent those infinite number of solutions, right? Remember, k can be any integer, whether that be -2 or -2000. Okay. All right, let's try another example. All right, so how about, let's say one where we have a composition as the argument of a trig function. So what I mean by that is, let's say we have, and first I want to find all solutions to the following equation. And we have sine of 2x equals to root 2 over 2. Okay. Now this 2x, I'm not going to worry about this till the very end, right? I'm going to right away just let u be equal to 2x. All right. And I just won't worry about that till the very end. So instead, what our focus is, our focus will be is solving sine of u equals to root 2 over 2. All right. And again, right, this is an angle in the unit circle. It corresponds to when sine is positive. Right, that happens in quadrant 1 and quadrant 2. Right, and those angles are when x is pi over 4 in quadrant 1, and in quadrant 2 we have 3 pi over 4. But again, the sine function is also periodic, right, with a period of 2 pi. So plus 2 pi k plus 2 pi k. Excuse me, this should be u. All right. Where k, again, is any integer. All right. Now, our goal is not to solve for it's to solve for x. So now let me go ahead and back substitute here, right? U is equal to 2x. So we have 2x is equal to pi over 4 plus 2 pi k, and 2x is equal to 3 pi over 4 plus 2 pi k. All right, and now I am going to solve for x, right, by dividing by 2, or division by 2 is equivalent to multiplication by 1/2, right? So I multiply both sides by 1/2. All right, again, make sure you include those parentheses because you want to multiply the whole expression on the right side of the equal sign. So here we have 1/2 times 2x simplifies to 1, so we just have x. When I distribute the 1/2, we get pi over 8, and 2 times 1/2 is 1, so we get plus pi k. And for our second equation, we get x equals to 3 pi over 8 plus pi k, right? And again, where k is any integer. All right, and now we have, I guess I'll include this part too. Now we have our solutions, all right? Pi over 8 and 3 pi 8. And in this case, every addition of a multiple of pi to pi over 8 or 3 pi over 8 will give us a solution. All right, let's take a look at the graph so we can kind of confirm our result here. So, all right, so our function changed from cosine of x to sine of 2x. All right, and our y was root 2 over 2. Okay, and our values for x became pi over 8 plus pi k. Okay, and set it equal to 0. Right away you could see we got our first one, pi over 8. Okay, and then our second value, 3 pi over 8 plus pi k, and 3 pi over 8 plus pi k. And here we go, right? The intersection of the graph. Right? And as k, we add those factors of pi in, gives us our next set of solutions. Or if we subtract those values, we get the set on the left side of the y-axis. Okay, all right. So that is how we solve an equation that has something that is more than just x as the argument of the trig function. Now, it wouldn't matter if it was, or let's look at another example where the argument of our trigonometric function is a little bit more complex, but we take the exact same approach of making a u substitution. And so for example, let's say I want to find all solutions to the following equation. Okay, secant of 1/3 x minus pi is equal to root 2. Okay, now for something like this, first of all, it's a secant function, and then we also have this expression as the argument. And again, I'm going to deal with this at the very end. All right, I'm going to start off by just making a substitution. Let u equal to 1/3 x minus pi. All right, so now we have secant of u is equal to root 2. All right, now when I'm dealing with secant and cosecant, I like to just try to, whenever possible, change it to sine and cosine by using the reciprocal identities. All right, so in this case, when I have one term equal to another term, the reciprocals are also equal to each other. So in this case, the reciprocal of secant of u is cosine u, and the reciprocal of root 2 is root 2 over 2, right? It's 1 over root 2, but you rationalize the denominator, and that leads you to this expression here, root 2 over 2. Okay, so now I have another angle in our unit circle, right? And we know that the cosine is positive in quadrant 1 and in quadrant 4. All right, and root 2 over 2 corresponds to a reference angle of pi over 4. And then the one in the fourth quadrant is going to be same reference angle, but the angle in standard position is 7 pi over 4. Okay, so again, right, we'll deal with this substitution at the very end. For now, we have u equals to pi over 4 plus every 2 pi k, right? The period of the cosine. And u equals to 7 pi over 4 plus 2 pi k. All right, where again, k is any integer. All right, so now once we have our solutions in u, now the next step is let's find these solutions for x by doing our back substitution. So we get 1/3 x minus pi equals to pi over 4 plus 2 pi k. And 1/3 x minus pi equals to 7 pi over 4 plus 2 pi k. Okay, and then we'll start off our first step here to solving for x. As we'll start by adding pi to both sides. Right, I'll solve these in tandem here. All right, so adding pi to both sides, this goes to 0, so we have 1/3 x equals to pi over 4 plus 2 pi k plus pi. Okay, now these are not like terms. If this didn't have the k here, then we would say 3 pi, but since that k is there, almost like our x, then we know those are not like terms. And our second equation is 7 pi over 4 plus 2 pi k plus pi. All right. And then the next step would be to multiply both sides here by 1, or divide by 1/3, which is equivalent to multiplying by 3. All right, so I'll multiply both sides by 3. All right. Again, don't forget the parentheses, so you know to distribute to all those terms. In both these equations here, we get x with a coefficient of 1. Distributing that 3, we get 3 pi over 4 plus 6 pi k plus 3 pi. Right? Just distributing out there. All right. Oops. And then for our second equation, we get 21 pi over 4 plus 6 pi k plus 3 pi. And again, where k is any integer. And those would be both of our solutions to our equation. Okay, so even if it gets really complicated in the argument of the trig function, again, wait to do that till the very end, right? Just make a quick u substitution and then solve it like we solved using some of the techniques in these past examples. All right, now, what if we have a value that is not on our unit circle? All right, so let's take a look at an example. Where we have sine, and again here the directions will be the same. We're going to find all solutions to the following equation. Okay, so sine of 2x equals to 87 hundredths. Okay, now 87 hundredths is not a value that I find on my unit circle. So I'm going to use my calculator to solve this equation, right? Now we have a 2x in here again. Worry about that till the very end, right? Let u equal to 2x. All right, so we have sine of u is equal to 0.87. All right, now I'm gonna use my calculator here. I'm gonna make sure I'm gonna solve it in radians. All right, and again, we have our inverse function here. So I can use the inverse like an operator. Sine inverse sine of u equals to sine inverse of 0.87. All right, and what this is going to give me is, remember, the inverse, the output of an inverse function, an inverse trig function is an angle. So it'll give me an angle that is in radians. So second sine inverse of 0.87 equals, and we get 1 point. Let's use, we're given 2 decimal places, so let's round to 2 decimal places. U equals to 1.06 radians. Now again, right, the inverse and our calculator does not tell the whole story. We need to be able to interpret this, right? Our calculator is very fast, but it's not very smart, right? You need to tell it exactly what to do, right? And even when it does give you a solution, we still need to figure out, all right, what does this solution mean? Okay, so the sign is positive in quadrant 1 and in quadrant 2, right? And it's also periodic, so we really have an infinite number of solutions, but I only get this value, this 1.06, right? So if we recall, the the range of the inverse sign is an angle between pi over 2 and negative pi over 2. We have a positive angle, so that gives me this value here, right? But I also know that this is a reference angle, so that's also this angle right there. Right, but I'd like the angle in standard position, so I need to find out what is that angle there. Well, if the full half revolution is pi, this angle here is pi minus 1.06. Okay, so now we have enough for both of our equations here. All right, so we have u is going to be 1.06 plus 2 pi k, and then our other one is pi minus 1.06. We're already estimating, so let's get a decimal approximation here. And we have 2.08. Okay, and again, k is any integer. All right, so I solved for u, but again, now what I was asked to do, I have the variable is x, so let's start back substituting here. So here we'll have 2x equals to 1.06 plus 2 pi k, and then 2x equals to 2.08 plus 2 pi k. All right, and let's divide or multiply both sides by 1/2. Or divide everything by 2. Okay, so over here we'll get x 1.06 divided by 2. We get 0.53. And then pi k, x equals to 1.04. When you divide it by 2, and then plus pi k, where again k is any integer. And those are our approximate solutions, right? Approximate because when we don't have exact values, right, then there's no choice but to round, which gives us a pretty decent approximation in this case. All right, so now we're going to do another example here, and we're going to look at equations that have multiple factors of either the same function or in some cases a different trig function, and how to approach solving those. All right, so the first one we're going to take a look at is an equation where we have two. So here again, for now we'll stick to finding all solutions. To the following equation. Okay, so the equation is 2 cosine cubed x equals to cosine squared x. All right, now a very common mistake that I see here all the time, all right, is we say, okay, I can divide by both sides by cosine squared x. This reduces to 1, and then here we have, there's 3 here, 2 down here, so we get a factor of 1 left, of 1 cosine, and then we have cosine x equals to 1/2. And then we're like, we have, all right, that's our solution there. And then we can approach this like that first example that we have. All right, so please do not solve a problem like this, right? The problem is we never want to divide by anything that has an x value. All right, because I don't know what x is, right? What if cosine of x is 0, and then I've eliminated some solutions, right? So I don't want to do that, right? The correct approach here, and in anything that has this type form where it looks like you can divide out a term, avoid the or resist the temptation to do that, right? Instead, what you want to do is you want to factor, right? You want to set equal to 0 and factor. So I'm going to subtract both sides by cosine squared x, right? These are not like terms, so I'm just going to rewrite this as and then cosine squared x minus cosine squared x gives me 0. All right, and I'm going to work with this, right, by factoring, not dividing, but factoring here. So I notice that these two terms, they have a common factor of cosine squared. Okay, so I took out a factor of cosine squared. That means if there are if this is cosine cubed, and I took out 2 factors, I have 1 more factor left. All right, now this is cosine squared, so I took that whole factor out. Now this does not become 0. We need a placeholder there, and that placeholder is going to be 1. All right, because when I distribute, I need to make sure that I get back exactly the same expression as above. All right, and if that 0 was not, if you put 0 there, then you would not get the same expression. All right, and of course equal to 0. Okay. All right, and now we have something where we have a product of 2 terms, right? This being 1 term here, cosine squared x, and this being the second term, 2 cosine squared x minus 1. Now, if I have 2 numbers that are multiplied together and give 0, what has to be true about one of them is that one of them must be 0, right? That's the only way we get a product that is 0. That happens either if cosine squared x is equal to 0 or 2 cosine squared x minus 1. Excuse me, this is a factor of 1. 2 cosine x minus 1 is equal to 0. All right. Okay. And now we have two equations that I can solve that are set equal to 0. Okay, so here we have take the square root of both sides. Normally when we take the square root of a square, we would write plus minus, but since it's 0, plus minus 0 is just simply 0. Okay, and for this one, we add 1 to both sides, divide by 2. All right, now you notice here that in our previous attempt where we divided by cosine squared, I simply got cosine x equals to 1/2, which I get here, but by dividing that cosine squared out, I completely missed that solution, and which would lead me to not completely solving that equation. All right, so now you can see why it's important that we do not divide out that cosine squared, but instead set equal to 0 and factor. Okay. All right. Now, excuse me. Now, when is the cosine equal to 0? That happens at these quadrantal angles, right? That happens at pi over 2, right? If we're dealing with the unit circle. And at 3 pi over 2. Right, now you can write the solution here in one of two ways, right? If we think of this, we could say, all right, well, I can write this as pi over 2 plus 2 pi k, 3 pi over 2 plus 2 pi k, right? This would be correct here to do, right? One other thing you can do is when you see the solutions, you can notice that for each factor of pi that I add, I get a solution, right? These are only pi radians apart, right? Pi gets me back here, subtracting those factors of pi always lands me on a quadrant, right? If I start off at pi over 2. So another way to represent this would be this. Both of these are equivalent. Okay? All right. All right, so now let's move on here to our second part here, cosine x equals to 1/2. Again, our cosine is positive in quadrant 1, quadrant 4. 1/2 corresponds to reference angle of pi over 3. And the angle in the fourth quadrant is 5 pi over 3. So we have as our solution x equals to pi over 3 plus 2 pi k to 5 pi over 3 plus 2 pi k. All right. And this we cannot write as 1 because they're not spaced out kind of evenly to get both of these solutions there. All right. Okay, so the next example that we're going to look at is, well, what happens when I have kind of a mix of different trig functions. All right, so let's say that now I'm going to switch up the type of solutions that I'm looking for. So I'm not going to find all of them, right, but I'm going to give you an interval where I do want to find a solution. So here I want to find exact solutions that lie on the interval 0 to 2 pi, inclusive of 0, but not inclusive of 2 pi. All right, so up to, but not including 2 pi. So let's start off by solving tangent squared x is equal to 1 minus secant of x. Okay. Now, as a rule, I would like to have my equation to all be in the same trig function, right? So if I'm dealing with cosines, I'd like everything to be in cosines. If I'm dealing with tangents, I like everything to be in tangents, etc. Right? That would be where I would like to start. Sometimes it's not always the case where you want that, but I definitely want to start there where I want to try to rewrite it in terms of just one type of trig function. Now looking at this, I have a tangent squared and I have a secant of x. Now hopefully when you see squares of trig functions, you right away start thinking of the Pythagorean identity. Right? So whenever I see a square of a trig function, I always think of my basic Pythagorean identity. Cosine squared x plus sine squared x equals to 1. And I know by dividing by the cosine squared of x, I get 1. Sine squared over cosine squared is tangent squared x. And 1 over cosine squared is secant squared of x. Now I like this. This is good, right? Because now I have a way to rewrite the tangent squared in terms of secant squared. And now I have an equation that's only in secants. Now one of them is squared and one of them is to the first power. But that's okay. I've eliminated at least having different trig functions. So if this is true, what also must be true is that tangent squared of x equals to secant squared x minus 1. And now I'll substitute, right? So here I'll have okay. And again, before I don't want to divide anything out, what I'm going to do is I'm going to set this equal to 0 and take it from there, right? So I'll start by adding secant of x, subtracting 1. So secant squared, secant are not like terms. So secant squared x plus secant of x. And then minus 1, minus 2. And on the right side, it's equal to 0. Now, when I have an equation like this, this reminds me of a quadratic equation. Right? Now, it's not a quadratic, but it is a quadratic type. Or in the sense, if we recall here, our quadratic equation looks something like this, where we have a squared term, the linear term in x, and then a constant. Well, we have that here, right? We have a squared secant, linear term of secant, in other words, to the first power, and then we have a constant. Right? I can also have a u substitution, where if I do that, if u is secant of x, then secant squared of x is u squared. Secant of x is u. And now I have a quadratic in u. And I can factor, or I can use a quadratic formula. I always like to factor. It always gets me to the answer easiest. And looking at this, as long as it's possible, right? Sometimes we can't factor and we are going to need to make use of the quadratic formula. But here, multiplies to negative 2, adds to 1. I think this should about do it, right? U squared, the first term, the outer term is 2u minus u, gives me a positive u. And in the last term, negative 1 times 2, negative 2. Okay. All right, and now we have, again, a product equal to 0. So what must be true here? Either u minus 1 equals 0, or u plus 2 is equal to 0. Okay, so u equals to 1, or u is equal to negative 2. All right, but again, I'm not solving for u. I have a function in x, and I want to solve for that. So I'll back substitute here, and we have secant of x equals to 1, or secant of x is equal to -2. All right, and again, here we have one term set equal to another one. Let me take the reciprocal here. So reciprocal of secant of x is cosine x equals to 1. And here we have cosine x equals to -1/2. All right. So when is cosine x equal to 1? Here we have a quadrantal angle, right? And it's equal to 1 on the unit circle when x is 0 radians. Now, it would happen every 2 pi, but as we were told here, well, I'm just looking for the interval between 0 and 2 pi, not including 2 pi. So there's really only one solution here. For this part, x is equal to 0, 0 radians. Okay, so our next one, cosine x is equal to -1/2. Cosine is negative in quadrant 2, quadrant 3. All right. And 1/2 corresponds to an angle on the unit circle, that angle being pi/3, our reference angle. In quadrant 2, that becomes 2 pi/3, and in quadrant 3 becomes 4 pi/3. Right? And those are the only solutions in the intervals 0 and 2 pi. So here we have x equals to 2 pi/3 and 4 pi/3. All right. Okay. And that's how we would find the solutions. Not all of them, but if we're just given a particular interval, that's how we would go about trying to find them. All right, let's try one more example here. Okay, so for our last example, here we want to find solutions, or find all solutions that lie in the interval (0 to 2 pi). All right, and our equation here is going to be cosine of 2x equals to cosine of x. All right. Now, it's important when you have something like this to realize is that when we're dealing with trig functions, we can't just start by dividing by 2 from both sides. We can't work inside the argument of the cosine, right? That's not the way that these trig functions work. What we can do is we can use identities, right? And we have a double angle identity, right? I could use that, right? I want, again, similar to when I said that I want my equation to be all in the same, in the same trig function, I would also like that here, right? Even though they're both cosine, this one is 2x and this one is x, so they're not the same. I want them to be exactly the same. All right, so we do that by using identities, right? So here, one identity is this one, but I don't like this one, right? Because now I am introduced a sine squared of x. But there are alternate forms of the double angle for the cosine, right? There's one that is strictly in cosine squared x. So I don't like this one, but I do like that one, right? 2 cosine squared x minus 1 is also cosine of 2x. All right, now we have something we can work with, right? And again, hopefully right away you should start seeing, oh, this almost looks like a quadratic type, like we did in the previous example. So what I want to do, I want to set this equal to 0, right? By subtracting cosine of x to both sides. All right, and then I'll treat it like a quadratic, right? So we're let u equal to cosine x. So we get 2u squared minus u minus 1 equals to 0. All right, and then I'll try to factor. So I think I can factor this one as well. All right. Okay, and here double check 2u squared. Outer one is minus 2u plus u gives me a minus u. And in the last term, plus 1 times minus 1, get negative 1. All right, excellent. And now let's, we have again a product set equal to 0. That means that, okay. So here we have u is equal to negative 1/2, u is equal to 1. All right, and back substituting. All right, excuse me, negative 1/2, and we've seen already here, cosine is negative in quadrant 2 and in quadrant 3, right, corresponding to values of pi over 3 and 4 pi over 3. Okay, and again, we're looking strictly for values between 0 and 2 pi, so those would be the only ones. Cosine of x is equal to 1. That corresponds when x is 0. And those are all our solutions in the given interval, that being 0 and 2 pi. All right.